All right, these additional notes will look at some of the things that we did in the textbook, but extend a few things a little bit further. So it'll be a good set of review and learning a few more things. There's a branch of mathematics that is called combinatorics, and combinatorics deals with all things that you count. And that is what we're looking at. So one of the first things that we looked at was the fundamental counting principle. The fundamental counting principle, you made a space for every decision that you had to make. So in this case, your new car is being built, you have to choose color, choose transmission, choose the interior. Then we put the number of choices in each space, multiply them together to find out that there could be 12 different cars that could be built. We're going to use the numbers 1 to 7, and some questions are you can use and repeat numbers as much as possible, but when you're choosing things from a list of objects, so if you weren't allowed to repeat, that's a permutation. Permutation saying you have the 7 numbers, you actually have them physically, and then you're trying to figure out how many different 3-digit numbers you can make. So if you weren't allowed to repeat them, does it make sense that you would have 7 choices for the first number? You could choose any one of those 7 numbers. But once one of them is used up, then you only have 6 left, followed by 5. And we learned that we could write this in permutations notation because there's 3 spaces starting with the number 7. If you were allowed to repeat, they would all be 7s, giving you 343 different possibilities. One of the things the textbook didn't do enough of is dealing with questions that have a restriction. So we're still going to use 1, 2, 3, 4, 5, 6, and 7, just like before. But we want to make it an even number. How many 3-digit numbers are even? So there's a restriction on the last decision. This number has to be even. The strategy is that won't be our last decision. That will now be our first decision. We will decide what number goes there first. If we look, if you want a 3-digit number to be even, does it make sense that it either has to end with the 2, the 4, or the 6? There are only 3 choices that could go there. Now, you've used up either the 2, the 4, or the 6. You don't know which one, but you've used up one of them. Does it make sense now you only have 6 numbers left than 5? Multiply this together, and there would be 90 3-digit numbers that are even if you only use the numbers 1 to 7. Why do you have to deal with restriction first? Well, don't write this down, but let's say you had your 3, and you knew this still had to be even, right? But you started with the first one. If you started with your first space and said, how many choices do I have? Any number could go there. I put 7. Then you'd say, well, I've used up one number. Any number here could be 6. But then you have a problem because you don't know what number to put there. Well, somebody would say, well, why can't I put 3? I say, well, what happens if you accidentally used up the 2? You could have used up the 2. You could have used up the 4 already, but you don't know. By putting the 7 and the 6, it says you've used up 2 numbers, but you don't know which 2 numbers. So you are unable to put a number at the end. But if we do the even number first, say I'm going to put either a 2, a 4, or 6 at the end, then whatever goes after that will work out fine. So the strategy of dealing with a restriction, you do that first. I want you to do this one on your own. We're still going to use just the numbers 1 to 7. But now the restriction is that it has to be odd. right, how do you do? If this is odd, and that's your restriction, 1, 3, 5, or 7, there'd be 4 choices there. Then you've used up a number 6, and then 5, to get 120 in total. But what I also want to show you with this question is a strategy that you are going to use in this unit called the NOT strategy. And the NOT strategy works like this. The NOT strategy, you count all of them and you minus the bad ones. So in our situation, we already counted all of them in example number 2. In example number 2, we found out that using the numbers 1 to 7 without repetition, there are 210 in all. Then we're going to subtract the bad ones. The bad ones would be their even numbers, which we counted in example 3. There were 90 even numbers. Does it make sense that if you took all the numbers and subtracted all the even numbers, that you would be left with all the odd numbers? And sure enough, the answer is exactly the same. Now, in this question, the way that we did it first, I think, is still the best. It's easy, it's not hard, deal with restriction first, but there are going to be some questions where the NOT strategy is going to be easier. It's going to be easier to count them all and to count the bad ones and subtract than it will be to count the good ones all at once. So we're going to see some examples where we use this NOT strategy moving forward. How many 3-digit numbers can be created using the numbers 0 to 9 without repetition? 3-digit number, 3 spaces. I want you to try it first on your own, and we'll go over it. All right, first question we have to have is something like 018 a 3-digit number? It's a 3-digit code. If you had to type in a code to get into somewhere, you could do that. But as a number, I would say that that's 18. We don't consider that different, and 18 is a 2-digit number. So we do have a restriction on this question that you can't start with a 0. And if the first one can't be a 0, there you would have only 9 choices. Now you've used up one number. How many choices do you have left for the next one? 9. Because you started with 10. 0 gets put back in, but one number is taken out. You have 9 again, then 8. For 648 in total. Okay, I want you to simplify these 3 without a calculator on your own. All right, let's see how you did. First of all, when simplifying factorials without a calculator, you start expanding the bigger one until you get to the smaller one. They'll simplify, and 7 times 6 is 42. Same thing in the second one. The biggest one is the 10. Start expanding that until you get to a smaller one. So I'm going to stop at 6 because that will simplify with the 6 factorial. The 4 factorial would be 4 times 3 times 2 times 1. And I'm going to color code this here. Can you see that 4 times 2 is 8? So the 4 and the 2 on the bottom would simplify with the 8. And the only number left on the bottom is a 3. But you can simplify it a fraction. If you had 9 over 3, that would simplify and leave you with a 3 in your numerator. Then what am I left with? A 10, a 3, and a 7 in my numerator. 10 times 3 times 7 is 210. So I color-coded it so you could visualize what canceled out with what. And finally, if you're simplifying and you have variables, again, expand the bigger one. N plus 2, 1 less would be N plus 1, and we keep going until we get to the number on the bottom. Your N factorials would cancel out. And if we expand this, you would get N squared plus 3N plus 2 as your final answer. So in our textbook, we looked at permutations. We're going to look at combinations later in this unit, and the order doesn't matter there. In permutations, the order does matter. So one of the things that we're really going to have to get good at is discerning, does the order matter in this question, or does the order not matter? So far, in all of the questions we've done, order has mattered. So if you wanted to rearrange the letters of A, B, C, well, you have 3 spaces. That would be 3 times 2 times 1, which is just 3 factorial, equal to 6. And if we wanted, we could list them all. A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. Wouldn't be hard, but the spaces lets us count it. We know that we should find 6 of them. So for permutations, we get the factorial notation. This formula is on your formula sheet. You might remember that this part was how many spaces, and this is the number that you start with. So we can translate the formula to spaces and fundamental counting principle, but we also have a formula with factorials as well. Should make sense to you that if you had n spaces and you started with the number n and just kept going down, like 9p9, 9 spaces starting with the number 9, 9, 8, 7, 6, 5, 4, 3, 2, 1. That would be 9 factorial. You ever notice how you can count backwards pretty quick? If I just do 9, 8, 7, 6, 5, 4, 3, 2, 1, pretty quick. How fast can you do the alphabet backwards? That's hard. We should have a contest. Who can say the alphabet backwards the fastest? I think I'm at Z and then it gets hard. All right. So for most permutation questions, you're going to use the fundamental counting principle. Here, 10 songs, we have 4 decisions. Which 4 songs are you going to make? 10 choices for the first one, then 9 choices, then 8 choices, then 7 choices. This is the same as 10p4. Where is it nice to use the 10p4? Well, if they had 100 pieces of music and we're going to make a 5-hour concert that played 25 of them, you don't want to write out 25 spaces. So then the formula might be nicer. But for most of our questions, it won't be that many spaces. You're going to find using the spaces, decisions, and choices easy. Well, this is a boring question. 4 letters, they're all different. It would just be 4 factorial, which is 24. Okay, so you imagine coming into math help, there are 12 desks. 5 students come in. How many ways can this be done? The number 1 mistake that people do in this question is they make 12 spaces. Because you're so used to putting students in desks, you want to make the spaces for the desks. But we have to remember, we make spaces for decisions. And here, each student that comes in makes a decision where they're going to sit. There would only be 5 spaces, not 12 spaces. So student number 1 comes in, How many choices do they have? 12. Okay? Student number 2 comes in. How many choices do they have? Okay, we are going to assume, because it's very awkward in math help, if there's one person in here and you come in and decide to sit on their lap. It's never gone well. It's like, what are you doing? So we're going to say, no, they don't come in and sit on the other person's lap. They have 11 choices, then 10, then 9, then 8. This is the same as 12p. And the P button is on your calculator as well, so you can find that on permutations. You could do 12 times 11 times 10 times 9 times 8, or you could do the 12p button. This is such a good question for today, because today is the 1st of June. We just had a new seating plan. How many different seating plans are possible? There are 33 desks, and there are 30 of you. So there would be, if I made the seating plan where I said, okay, just line up in the hallway, first person come in, sit wherever you like, next person sit wherever you like, there would be 30 spaces, starting with 33 choices. 33p30. That is a lot. If I go to my calculator, and I put that in, oh my goodness. This is the number that I get. About. The last bunch of zeros aren't actually right. I just rounded because my calculator doesn't show them. There's a huge number of seating plans. One year I had a competition. I said, I just made the seating plan random on my computer, and where everybody's going to get a chance. So starting with the person who's sitting there, who do you think is going to sit here? Ben goes, I think it's Sam. And I would say, no, you're wrong. And this competition, if you get it right, you get 100% in the math class, don't have to come again. Okay? It's a pretty exciting competition. You're like, yeah, final grade in math, 100% grade 12 pre-calculus, don't have to write any more tests or anything. Okay? I had a pretty good chance that no one was going to get it, because that's a huge number. Now, you have to, was this mean? You have to decide, because it came, maybe it was Jack's turn. And Jack said, no, I think Chelsea's person. I said, yes. It's like, oh. And I made him go through the whole scene, and I was like, yes. All the way to the last one wrong. The last one, no. And then I put it up. I said, just kidding, you didn't get it right. Was that mean? That was too, I shouldn't have done that. Okay, we also did, and I want you to change this because I think the textbook has a better name for this than I like that they call this identical objects. So change that title to permutations with identical objects. These are the questions where the letters repeat themselves, right? This is where we had a problem with Tanisha the other day. I don't think we figured it out. So if you have something that repeats itself and you want to count the permutations, then you divide by the repetition. So for us to sit here, 1, 2, 3, 4, 5, 6, 7, 8, 9. Normally 9 letters would be 9 factorial, but we have 3 S's, 3 factorial, 2 I's, and 2 P's. If you ever wanted to show your work, this is all I would expect. Wow. Did anybody realize I just did that? What number should be here? There's 2 P's to get your final answer. make sure if you are typing that into your calculator, either use the fraction button or you'd have to put brackets on the bottom. I find that if I'm typing this into my calculator, the factorial button takes so long to find. Well, it doesn't take that long, but it's kind of annoying to find. I have some of these numbers, 6 times 2 times 2. Like, they're so easy to figure out. It's quicker to type the actual numbers in rather than type the factorial sign, especially something like 2 factorial, which is equal to 2. Don't waste your time finding that factorial button. Just type it in directly. So we have to recognize when a question is an identical objects question. So, and then once you recognize it as an identical objects question, you try to make some word using letters that has those letters repeated. So this one, we've got 3 of model A, 4 of model B, and 2 of model C. Here's our word. And then we just need to count, well, how many letters are there? There's 9 letters in total. We have 3 A's, 4 B's, 2 C's. And we can just multiply and divide out those identical objects. So you have to be able to read the question and discern, is there identical objects in this question? Then I do it like a Mississippi question, right? Some of the harder ones, we saw one like this in our notes. John lives 3 blocks. Let's make our city blocks here. John lives 3 blocks north and 6 blocks east. So this is his home, and this is the school. And if he needs to go from school to home, he's going to go north 3 times somewhere, and he's going to go east 6 times. How would we count it? Here's our new word, right? And we need to 9 factorial, 3 n's, 6 e's. Type this into our calculator, 84 ways in total. Okay? Now, we also learned that you could count the individual pathways all the way to the end. Now, if you're just going in one direction, probably the letters is the easiest. But if there was a situation, okay, we're going to add a situation here. We're going to add a situation right here. That's Betty's house. And now something's happened, and every time that John walks home from school, he always walks by Betty's house. So what does that mean for counting? Well, we would have to take out certain sections. So it makes sense that he never goes to these spots anymore and never would go to those spots if he's always walking past Betty's house. So this would be one where we would count pathways. There's 1 pathway here, 1 pathway here, 1, 1, 1. And you can count the pathways to a new intersection by adding the 2 previous ones. So this will be 2, 2 plus 1, 3, 2 plus 1, 3, 3 plus 1, 4, 3 plus 3, 6, 4 plus 6, 10. There'd be 10 ways that John could get to Betty's house, and then going home after that, does it make sense that this number will be 10 because it's 10 plus nothing? And this one will be 10 because it's 10 plus nothing, 10 plus nothing, but this will be 20, and this will be 30, and this will be 10 plus nothing. And there are 40 ways that John can now get home John has to walk past Ben's house. Now we could add a situation here where you could use the not strategy. Something happens, and John is no longer allowed to walk past Betty's house. So we could use the not strategy. How many ways could he get home if he is not allowed to go past Betty's house at that intersection? Well, we could say there's 84 in total. We counted that there was 40 that went past Betty's house. Does it make sense that there would be 44 ways that he could walk home if he's not allowed to go past Betty's house? That would be the easiest way to solve this question now. The other thing you could do is you could we could block that one out and do 1, 1, 1, 1, 1, 1, 1, 1, 1, add. Did I add up something wrong? Oh. 7, this is 18. I made a mistake in adding somewhere. Because it should come out to 40. Oh, it does. I just didn't add the last ones up. Comes out to 44 that way as well. But there is a spot where if you did the preliminary work, the not strategy would be better, rather than recounting all of this. Okay, this is where we're going to stop for today.